Superconductors are a nice idea in principle. In practice, they're really cumbersome to use. But what if I told you that there's a company which thinks they know how to make the electric grid superconducting? Yes, there is. Let's have a look. A superconductor is a material without electric resistance. Within a superconductor, electric currents can travel entirely without loss. Superconductors also have the odd property that magnetic field lines can't enter them, which is why they float on magnets and are used for magnetically levitating trains. The problem is that all known superconductors either require very low temperatures or high pressure to work. The most practical ones are at the moment the so-called high-temperature superconductors, which become superconducting at temperatures above minus 196 degrees Celsius. Minus 196 degrees might not be your idea of a high temperature, but at that temperature, the material has the advantage that it can be cooled with liquid nitrogen. The ones that are superconducting at lower temperatures are much more difficult and also more expensive to cool. But that is only part of the problem. The other part of the problem is that the known high-temperature superconductors are difficult to produce and brittle. It's not like you can just draw them into wires and ship them. If you remember last year's episode with the LK99 superconductor that wasn't, that'll give you an impression. Remember how laboratories all over the world were baking stuff for several days and then they had a few crumbles at best? Yeah, even if the stuff would have worked, it'd be hard to make power lines from that. But superconducting power lines do exist, and some of them are actually in use. They work completely differently from normal wires though. In a normal wire, you have, say, copper in the middle and then an insulation around that. In a superconducting wire, you have different layers through which the coolant is pumped and then the superconductor itself is wrapped around this. It typically looks like you see in this image. It's like a burrito, but instead of beans and cheese, it's filled with the hopes and dreams of electrical engineers. And yes, those do work, but the issue is that producing liquid nitrogen requires energy, and if your goal is to make power transfer more efficient, then it doesn't make sense if you put more energy into the cooling system than you save during transfer. There's also the issue that as the nitrogen flows along the cable, it warms, so it has to be recooled at regular intervals. For high power lines, this is typically every 5 kilometers or so. It's cumbersome to build and costly to operate. But the American company Via says they know how to change that. They're located in Massachusetts and have been making headlines a few times in the past years because they've attracted substantial funding and had a demonstration project. But exactly what they want to do has remained somewhat unclear. However, I've now found both a paper and 2 patents that I think explain what they're up to. It's like I'm a detective, but instead of solving murders, I'm unraveling the mysteries of really cold wires. To unravel the first mystery, the company Via derives its name from Ohm's law, that is V equals I times R. They're using an idea that came out of Los Alamos in 2010, which is to not pump liquid nitrogen around, but instead let it evaporate. You can see a sketch of the idea here. This has the advantage that you get an additional cooling just from the evaporation, which is much more efficient. It works much like if you're wet, then the wind feels much colder because it makes some of the water evaporate. In 2 patents which the company has filed, they lay out their design for the cooling system along the route and also the suspension system for overhead cables. It's basically a design to pump some of the nitrogen out of the cable, push it through a cooling system, and then pump it back into the next segment. The nitrogen itself can be extracted from air, which is 78% nitrogen in any case. They've claimed that with this system, it could be sufficient to have a cooling station every 100 kilometers or so, though I suspect that this is overly optimistic. Using these cables would not only avoid losses from the resistivity of the cables, superconducting cables can also carry more power because they don't get that hot. So if we were to use those cables, we'd need fewer of them in the first place. Their test project spanned just about 30 meters, but they've partnered with the National Grid, that's an energy company which operates both in the US and the UK, to test their idea over larger distances. Imagine how rich these guys could get if the entire world were to use that. But you saw it coming, there are a couple of problems. The obvious one is that no one knows how reliable such a system would operate on large scales. Also, high-temperature superconductors are currently more expensive than standard cables, and there aren't a lot of suppliers for them either. There's also the question of how to deal with icicles that are likely to form on power lines. Also, I'm wondering what had happened to birds if they try to sit on the cables. Will their feet freeze to the cables? That'd be really, really unpopular. Though maybe it's just a matter of marketing. Cryogenic pigeons coming soon to a power line near you. The 2024 Nobel Prize in Physics did not go to physicists. It went to two computer scientists for developing the first neural networks, which became the basis of what we now call artificial intelligence. If you still doubt that physics is in crisis, the fact that the Nobel Prize in Physics goes to computer scientists should make you think. Really, I'm just grumpy because all my predictions were wrong. I guess my crystal ball needs a software update. So let's have a look at who was awarded what for which work. The Nobel Prizes went to John Hopfield and Geoffrey Hinton. Hopfield is an American computer scientist who developed the first neural networks known as Hopfield networks. These networks are algorithms that represent nodes with connections. The nodes have values assigned to them called weights. This loosely resembles the architecture of neurons in the human brain, hence the name, though Hannibal Lecter said the computer version doesn't taste as well. The Hopfield networks were basically a way to store patterns from data that you fed into them, and then you updated the weights. Later, you could take a new pattern and ask the network how close your new pattern is to what's stored. These Hopfield networks could learn, if in a very limited way. They were far from the neural networks that computer scientists use today, but they had the basic idea of weights and connections and an updating rule. Hopfield came up with this in 1982. When Hinton heard of this, he basically immediately started to try and improve the Hopfield networks. Hinton, who is British-Canadian, had the idea to give the deterministic Hopfield networks that follow strict rules a probabilistic element that much improved their ability to learn. In 1985, he published a paper about this titled "How I Plan to Screw Over Physicists by Winning Their Nobel Prize." Just checking if you're listening. It was titled A Learning Algorithm for Boltzmann Machines. It's called a Boltzmann machine because it uses the Boltzmann distribution from statistical mechanics. These ideas laid the basis for neural nets, though the breakthroughs thanks to which they became so widely used came much later. What made neural nets so powerful was adding multiple hidden layers that are the deep neural nets and backpropagation, which basically means you go back and adjust the weights after you've learned whether the results are any good. Geoffrey Hinton worked at Google for a long time but left in May 2023 because he began to seriously worry about the risk posed by AI. In his own words, he wanted to be free to speak about this. He since swore that we are breeding a superior species that we won't be able to control. In the Nobel Prize announcement, the committee stressed that neural networks have been very useful in physics. They probably said that because they anticipated that some physicists would be annoyed. But it's true, of course. Neural nets are now used pretty much everywhere in physics. They're used for data analysis, for modeling, for analyzing data that was produced by neural nets. It's neural nets everywhere. They've had a major impact on physics, no doubt. It's like the glitter of the scientific world. Once you let it out of the box, it's everywhere and you'll never get rid of it. But are neural networks physics? Well, they run on computers, which are made of microchips, which are made of particles, which is physics. So sure, neural nets are physics in some sense. Though by the same argument, everything is physics, including your grandma's secret cookie recipe, and Elsevier would really like to publish it. There's also a fair argument to be made that physics is really not so much about what you describe, but about how you go about describing it, the way that you use mathematics to describe a system, which is why you can use physics to describe traffic or the spread of fake news on social media or the growth of cities. Or maybe that was computer science. I'm getting a little confused now. But let's be honest, software development is not what we traditionally think of as physics. Among the disciplines that get Nobel Prizes, physics was arguably the closest for this topic, so it makes sense that the Nobel Prize Committee would lump it into physics. But this tells us two things. First, it tells us how terribly behind the Nobel Prize Committee is on awarding prizes, because it's not like neural networks or machine learning is new. As they themselves noted, it's been used in physics and many other disciplines for decades. It just didn't occur to them to reward a prize for it until everyone was using ChatGPT. Second, it tells us that there was no topic in real physics that was even remotely comparable in relevance. So please excuse me now, I have to go and quietly weep into my quantum mechanics textbook. Scientific fraud is a huge problem, and I'm afraid it'll become much worse. It's no longer just a problem in academia. Increasingly, it's also spilling over into everyday life. A recent investigation revealed some questionable research practices at the Stanford Healthcare Innovation Lab, SHIL for short. It's located right next to the Stanford Center for Proved Misconduct, SCAM for short. No, I made this up. The last one. The SHIL Institute is totally real. They ran a few psychology trials with rather small sample groups, showing that a 6-day course by the motivational speaker Tony Robinson is super effective at treating depression. According to the San Francisco Chronicle, at least one of the studies was funded by Robbins Research International, owned by the very Tony Robinson whose course was the subject of the study. Maybe a mild conflict of interest there? What do you think? Okay, you might say, but everyone knows that half of psychology is pseudoscience anyway. But how about this? Remember curcumin, one of the ingredients of an Indian spice called turmeric? Yes, that yellow stuff that you've been told is supposedly good for your health. If you Google it, you'll find loads of websites claiming many high-quality studies show that it has major benefits for your body and brain, and similar things. Unfortunately, it's not true. This is a myth which goes back to Bharat Agarwal, an Indian-American biochemist who worked at the University of Texas. He published dozens of papers about the supposed benefits of curcumin. He even wrote a book about it. But following the publication of the book, some people had a close look at the papers, and they found clear evidence of repeated research misconduct, notably image manipulation. A whopping 65 of his papers were retracted. Other studies later found that curcumin does very little, if anything. That's primarily because it's not absorbed by the body, though adding other substances to it might improve the absorption and benefits. You might say, all right, but at least no one got hurt. Well, the US National Institute of Health spent more than $150 million to study the stuff, and lots of people bought it. They probably still do. This curcumin tale has been so widely spread across the internet that it's basically impossible to debunk. What happened to Agarwal? He retired in 2015 and published some more papers, some of which have been retracted. A more recent study of scientific fraud that's even more depressing is that of Eliza Maslaya. Until just a few weeks ago, he was head of neuroscience at the National Institute of Aging in the United States. He was a very big name in Parkinson's and Alzheimer research. But according to a recent report in Science, a whopping 132 of his published research papers have suspicious images images and have been flagged for possible misconduct. This includes some work that's been the basis for drug trials on Parkinson's treatments. Already 2 years ago, a prominent researcher who worked on Alzheimer was accused of misconduct in at least 25 papers. Some of his research had laid the ground for the most widely pursued hypothesis for how Alzheimer comes about, namely by building up a protein called beta-amyloid in the brain. Drugs were developed based on the idea and went to trial. They didn't work. People who were in those trials wasted precious time, and both public and private money went into useless research. Scientific fraud and sloppy research affects all of us. In the worst case, people get actively harmed. Remember Didier Raoult, who pushed ivermectin as a cure for COVID? Tens of thousands of people, including many children, died because they didn't receive proper treatment. It doesn't just happen in medicine, of course. There are frauds going on in photovoltaic research and in material science too. A paper which just recently appeared on the archive identified more than 2,000 cases in which electron microscope images were being faked. This shit is all over the place. The really depressing part is that a lot of the fraudulent studies were only identified because of image manipulation so obvious you can spot it by eye. Fraudsters often just copy and paste the same image into multiple papers, and some eagle-eyed science detectives have specialized in spotting this. There's now an entire group of them working on identifying mass fraud. I recently talked to one of the science detectives, Reese Rickardson, and he told me that they're finally getting funding from research institutions. I think this is really good news. We need more of this because AI-generated images become more and more common, and scientific fraud is becoming so much worse thanks to this. I always wonder why people do that, and I'm afraid the answer is cynicism. An increasing number of scientists think the system is unfair and good work isn't a winning strategy. They think everyone cheats and that justifies their own cheating. On top of that, there aren't many penalties, really. Papers will be retracted and people might be forced to prematurely retire, but then they can relax on their cozy pension. Tony Robinson's depression curing course, by the way, costs $4,500 and his estimated net worth is $600 million. I think he owes me for making depressing videos. I don't know about you, but I've become rather disillusioned with artificial intelligence. Text generation is meh, fact-checking meh, images meh. And what are companies doing about it? They're just making their models bigger. It's like particle physics. If it doesn't work, do the same thing again, but bigger. Meh. There's been one thing that people told me AI is genuinely good for: writing computer code. But several studies have now appeared which looked at this, and the news aren't good. Let's have a look. In the past years, I've heard quite a few software engineers say that the future of software development is coding in English. Young people won't have to learn how to code, and everyone's a software developer now. The first time I heard about this, my reaction was meh. That's because I think about computer code as mathematics, not as spoken language. Code has strict rules and precise definitions. If you throw a lot of code together and feed it into a large language model, it's like handing gourmet recipes to a fast food chain. You just know the result will be deep fried. This happens just the same way that these models blur out how we individually use words, each with slightly different meaning, and then they create one common hodgepodge that lumps us all together with mediocre results. The idea that you can convert something as vague and imprecise as human language into code just didn't make sense to me. But I'm not a software engineer, and I saw some demos that honestly impressed me. I also personally know people who told me that ChatGPT is saving them tons of time by spitting out Python code that they can just copy and paste, and I've no reason to doubt it. So this was quite a wake-up call for me. Just a few weeks ago, a group of computer scientists published the results of a study that evaluates the impact of generative AI on software development productivity. They did 3 random controlled trials that, among other places, were conducted at Microsoft. In the abstract, they say that using generative AI in software development increased productivity by 26%. When you look at the paper more closely, though, it turns out that by productivity, they mean the number of pull requests. This sounds like an unpleasant conversation with a dentist, but what it means is that a change or addition to the code is ready to be pulled into the main project. The reason this is the task they mention in the abstract is, as they explain in the paper, only the effect on the number of pull requests is statistically significant at conventional significance levels. If you break it down by junior and senior level, then at the senior level, there's barely any gains. And this is one of the better findings. Another recent study from UpLevel followed 800 developers from January to April this year. They found no significant changes in efficiency, but a 41% increase in bugs. Another study from GitClear says that the most marked change they've seen is a steep increase in copy and paste operations and more mistakes in the code that later have to be fixed. And an earlier study found that coders who use AI write less secure code, basically because they trust AI too much. That doesn't sound all that great. So what does that mean now? There are probably some coding tasks that large language models are good for, but it seems that they're much more rare than we wished and hoped. The current models are useful to get novices up to speed, and that's good. But beyond that, they're mostly providing advanced templates that have to be adjusted, frequently so much that skilled coders are better off just doing it themselves. It's not the game changer it's been made out to be. One of the most plausible applications is probably the design of websites with standard elements. This type of application already exists. Just for your entertainment, this is an example in which I've used a platform called Wix to generate a website for my great upcoming pet grooming salon. And here's the website it has generated, all including images for bunny harnesses, a book that doesn't exist, and fake customer reviews. This mere result of generative AI encoding supports the skepticism from some reports earlier this year, which said that the economic impact of AI in the near future has been vastly overestimated and that consequently most AI companies are currently overvalued. These new studies won't reassure investors. I still think there's a real possibility that AI capabilities will make a significant jump in the near future and will get to human-level intelligence rather suddenly. But at the moment, using AI is like using a chainsaw to cut butter. It gets the job done, but someone's got to clean up the mess. One of the most surprising physics discoveries I've seen in my lifetime was dark energy. It was so surprising that the first time I attended a seminar about it, everyone was sure this was a measurement error. It wasn't. Dark energy seems to be real, but physicists have no idea what it's made of. In a recent paper, two physicists now claim that it isn't made of anything, but instead a consequence of our universe being holographic. Let's have a look. Genuinely new ideas are rare, but the idea that the universe and everything in it is really a sort of hologram is such a rare new idea. It's called the holographic principle. It was put forward in the early 1990s by Gerard Toft and Lenny Susskind, one of whom has won a Nobel Prize, and the other was recently called an asshole by Eric Weinstein.
This is basically the attempt to take a school massacre and plead to a parking ticket. And no, I think that the prosecution should decline the offer from the good Dr. Susskind and say, no, you have 40 years of the destruction of your colleagues to answer for. You've chosen to be, words fail me, an asshole.
According to my new idea, podcasts are a sort of hologram too. They actually happen in an entirely different dimension. If the holographic principle was right, it'd mean that everything which goes on inside a volume of space can be entirely described by what goes on at the boundary of that space. It's like the universe is a box of cereals, one that doesn't only have the ingredients listed on the outside, but also how the nuts move around if you shake the box. The idea came out of black hole research because it seems that the amount of information that a black hole can store doesn't scale scale with its volume, but rather with the surface area. Toft and Susskind then said, well, what if that's true not just for black holes, but for every volume? Cereal boxes, planets, the entire universe. That's the holographic principle. It's a bold and quite audacious claim, because if it was true, this would mean that the information about what goes on inside the universe is highly compressible. You don't need to track what's going on in some part of three-dimensional space. All you need to know is what's going on at the surface of that space. By the way, this video comes with a quiz that lets you check how much you remember. What does any of this have to do with dark energy? Dark energy is whatever's causing the expansion of the universe to get faster. Astrophysicists have measured how the expansion is speeding up, and that gives us a value for dark energy. The curious thing is that this value is roughly the inverse of the square of the radius of the visible universe. In other words, it's proportional to 1 over the surface area. Ah, surface area. Coincidence? Yes, it could just be coincidence, or maybe dark energy is actually a consequence of the finite size of the observable universe, and it comes from the boundary. You see, in our mathematics, the universe is infinitely large, but we can only observe part of it. That's because the universe has only been around for about 14 billion years, and we can only see galaxies whose light had time to reach us. This is why the universe has what's called a cosmological horizon, a limit beyond which we can't see. The idea of holographic dark energy now has it that this boundary, the cosmological horizon, gives an energy to empty space because it cuts through quantum fluctuations so that they can no longer average out to zero. The larger the volume, the less you notice that. The resulting energy of empty space is proportional to the inverse of the size of the boundary. And this energy behaves kind of like you expect dark energy to behave. It's not constant, as is often assumed, because the size of the universe increases, but it changes slowly enough so that it fits the data okay-ish. This idea isn't new, it's been around for 20 years or so, it's just that physicists thought it doesn't work, because a vacuum filled with such holographic dark energy wouldn't be stable. This means basically if you have some small random change, it'll create more energy from nothing and everything will fall apart. And this is where the new paper comes in. The authors are saying that the earlier claims about instability didn't make sense, because normally you do this by asking, what if I make a small change here? Will it fall apart? But for this holographic energy, they say, you need to make that small change so that it's consistent with the holographic property of the stuff. It's a very non-local change, really. They arrive at the conclusion that, contrary to what we thought for 20 years, this idea might work after all. It's kind of like losing your keys and finding out they were in your pocket the whole time. I've always liked this idea because I feel like we're missing something big about the quantum properties of space, and maybe this holography idea is it. Then again, if you look at the details, the link between the holographic principle and this type of dark energy is somewhat sketchy. So I want to see better maths before I buy into this. Until then, I guess I just have to open the cereal boxes. Thanks for watching. See you tomorrow.